In this video, we discuss scientific notation. Often when measuring or counting very large or very small quantities, scientific notation gives us a more efficient way of writing and communicating numbers. Scientific notation has two parts. First, a number that's between 1 and 10, which we call A. So it's greater than or equal to 1 and strictly less than 10. So that gives us a number that is pretty manageable. The second part is 10 raised to a power. 14,200. If we convert that to scientific notation, first we note that this is not a number between 1 and 10. So what we'll do is we'll move the decimal point until we get a number that's between 1 and 10. So if I move that decimal place once, 2, 3, 4 times, I have a number that's between 1 and 10, 1.42. Now, 1.42, of course, is less than 14,200. I'm not trying to get a different number. I'm trying to get a different form for the number, for the same number. So we have 1.42 times 10, and since 14,200 is larger than 1.42, we're going to have 10 to the fourth power, because we moved the decimal place 4 times. 1, 2, 3, 4 times. So 1.42 is a number between 1 and 10. So that's the A times 10 to the power 4. We can also take small numbers and do the same with them. So 0.0042 is not between 1 and 10. So I'm going to move the decimal place 1, 2, 3 times to get a number that is between 1 and 10, 4.2. So it's going to be 4.2 times 10, but since 0.0042, since 4.2 is larger than 0.0042, we have to write that with a negative exponent, because 0.0042 is a small number. So 4.2 times 10 to the negative 3 is equivalent to 0.0042. The next three examples are perhaps even better examples of why the scientific notation is efficient. These next numbers are getting fairly large and fairly small. So we have 24,396,500. Obviously, it's not between 1 and 10. So what we do is we start moving the decimal place until we get a number that's between 1 and 10. 1, 2, 3, 4, 5, 6, 7. So I have to move that 7 places. Once I do that, I have 2.43965. We can drop those zeros there. That is a number between 1 and 10. So we have the first part, then we're going to go times 10 to the 7th power. It's because we moved the decimal place 7 times. 0.00062. This is also not a number between 1 and 10. So we're going to move it 1, 2, 3, 4 places, the decimal point. Okay, so we have 6.2. Now 6.2 is larger than the number we started with, the 0.00062. So I need to make it smaller by using a negative exponent. So we'll go negative 4. That negative tells us what direction the decimal point was moved. The last number, probably the best example of why scientific notation is efficient. We have a lot of zeros there. You can imagine that would be very easy to miss a zero when you're writing, right? So to put this in scientific notation, again, we need a number between 1 and 10. This is not between 1 and 10. This is much less than 1. So we start moving it 1, 2, 3, 4, 5, 6, 7, 8, 9 places. That gives us 9.4, which is much larger than what we started with, right? So to make it equal to what we started with, we're going to go times 10, but to a negative 9 power there. We can also go in reverse. If we're given scientific notation, we can convert it back to standard notation. For example, 3.21 times 10 to the 5th power. So we'll take our 3.21. 10 to the 5th is 10 times itself 5 times. That's a large number. It's certainly larger than 3.21. So the 3.21, we're going to make it larger by moving the decimal point. So that means moving it to the right. And we're going to move it 5 times because that's the exponent on the 10. So we're going to go 1, 2, 3, 4, 5. So that gives us 3, 2, 1, 0, 0, 0. So 3.21 times 10 to the 5th is 321,000 in standard form. Both forms are useful. We like the standard form. We like the scientific notation. The next example, we have a very small number, 7.4 times 10 to the negative 6. So that means we're going to be making 7.4 smaller, right? 7.4 is larger than 7, is a large number relative to 7.4 times 10 to the negative 6. So to make it smaller, we're going to move that decimal point 6 places to the left. So we get 1, 2, 3, 4, 5, 6. So 0.0000074. When you're using your calculator or GeoGebra, they'll often use a capital E to stand for scientific notation. That'll stand for the times 10 part. So for example, E8, if you see E8 on a calculator, then that often is standing in for times 10 to the 8. E negative 12, that's probably telling you it's scientific notation and it's 10 to the negative 12. Let's practice with some outputs from GeoGebra. So if we're given 2.5 times 10 to the negative third, that means we have a relatively small number. 10 to the negative 3 is we have a number being divided by 10 3 times. So we're going to take the 2.5 and make it smaller by going to the left. We're going to go 1, 2, 3 times. So we have 0.0025. The next example, we see the capital E notation. So we have 6.3158 E negative 12. So that's telling us times 10 to the negative 12 power. A very small number, right? So 6.3158 is large relative to what we started with. So we need to make it smaller. We're going to move the decimal place 12 times to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 0.000000000063158. You can see why scientific notation is often preferred, because it's easier to keep track of the digits. If you have lots of zeros, the scientific notation is easier to keep track of those. In the last example, we have times 10 to the 6th, so that means we have a relatively large number, so we're going to take our 3.92518 70412, and we're going to move it 6 places to the right, because 3.92 is much smaller than 3.92 times 10 to the 6th. So to make it into standard form, we're going to go 1, 2, 3, 4, 5, 6. So we have 3925187.0412. in the standard form.